So now suppose we want to find the area of the region inside the circle, r equals 3 sine theta. So that equation might not scream circle to you, but we can talk about that. And outside the cardioid, r equals 1 plus sine theta. So now we want to find the area between two polar curves. Okay, so first of all, my claim about this being a circle. R equals 3 sine theta. So notice if you take that equation, here, so I'll put circle in quotation marks, like we're not really believing it. R equals 3 sine theta. If we convert this to rectangular form to make it more familiar to us, the way to do that is to multiply both sides of the equation by r. You may have seen that in a previous video as a way to help convert between polar form and rectangular form. So if you multiply both sides of this equation by r, you'll have r squared equals 3 times r sine theta. R squared is equal to x squared plus y squared. And r sine theta right here is equal to y. So now we've got the equation written in rectangular coordinates. Now to put this equation of a circle in standard form, we should move the 3y over. So x squared plus y squared minus 3y equals 0. And then if you recall that the standard form for the equation of a circle is x minus h squared plus y minus k squared equals r squared. This is where the center is hk and the radius is r. So in order to get an equation like this into that form, I need to complete the square in this y squared minus 3y expression. The x expression here is already a perfect square, just x squared, so that's nice. But the y expression, we need to add that magic number that'll complete the square on this side of the equation and then balance it by adding that same amount to the other side. So you might recall the key to completing the square is you take this coefficient of y to the first, so in this case -3, divide it by 2 and square it. So that'll be 9 over 4. That's the amount that you should add to both sides of this equation. And then I'll come up to the top of the board here. So that means we have x squared plus y squared minus 3y plus 9 over 4 equals 9 over 4. This expression right here, the shortcut for factoring when you complete the square, is it's going to be y and then half of this coefficient, minus 3/2 squared, equals 9/4, which is 3 over 2 squared. Notice if you double check this, if you write out y minus 3/2 times itself, you will actually get y squared minus 3y, because you'll have minus 3 over 2 minus 3 over 2. When you combine, you'll have minus 3y plus 9 over 4. So this is a circle. Let's see, I want to draw the graph. Centered at x coordinate is 0 because there is no h here. Y coordinate of the center is 3/2 and the radius is 3/2. So if I draw that graph down here in the corner, whoops. Let's see, so let's say this is 1, 2, 3 units right here. The center is at 1.5. So x coordinate is 0, y coordinate is 1.5, so that's here. Radius is 1.5. So if I go 1.5 units down, 1.5 units up, and then 1.5 units to the left and right, which I guess I'll label here. So 1.5 would be about here. Oopsie. Same, I'm going to keep the same y. Let me see if I can do that a little better. 1.5 units to the left. Draw the circle. There we go. So there's your graph of r equals 3 sine theta. And it is a circle. Okay, great. With the cardioid, I mean, I'm going to mostly take their word for it on that graph. But if we think about plugging in values, so starting with, if you plug in theta equals 0, sine of 0 is 0, and so we get r equals 1. So we're going to start here. As you increase theta, think of a unit circle, as you increase theta from 0 to pi over 2, the value of sine increases towards 1. And so you'll have a maximum value for sine theta of 1, plus 1 here, so 2. And that's going to occur when theta is pi over 2, right? That's when you're up here. So at pi over 2 radians, so that's this ray here, we get a maximum value of 2 on that cardioid. So it's kind of going around like this. And then it's going to come back down. It's symmetric. It's going to come back down to this -1 position here. And then it does the kind of top of that heart shape down here. So that'll be the graph in red there of r equals 1 plus sine theta, the cardioid. So there's your two graphs. So now we at least maybe can kind of look at the region we're trying to find. Now be careful about how these are described. So we want to find the area of the region inside the circle, so inside the blue, and outside of the cardioid, outside of the red. So inside the circle, outside of the cardioid, that's going to be this region here. So this is the region where it acts to find area of. Again, I would be inclined to use symmetry. So when I set up limits of integration, I'm going to want to integrate from this theta, whatever this is. This is going to be alpha, my lower limit of integration. And I would integrate up to pi over 2 radians right here, and then just multiply by 2 to get the total area. So that's the plan. Now, to find that lower limit of integration that I've labeled alpha over there, let me put that here. So finding that value of alpha, we need to find the intersection of those two graphs. So and I want to keep these color-coded, r equals 3 sine theta for the circle, and r equals 1 plus sine theta for the cardioid. So in order to find the intersection, we're looking for r theta pairs that are common to both graphs, right? Because this point of intersection right here is a r theta pair that lies on both graphs. So it's an r theta pair that satisfies both of those equations. And so to find that intersection, we can say, okay, well, if it's the same value of r along both curves, then I could set these expressions equal to each other. 3 sine theta equals 1 plus sine theta. And so now if I subtract sine theta from both sides, I have 2 sine theta equals 1, divide by 2. So I want to know, when is sine theta equal to 1/2? And again, lean on the graph if a graph is provided. I know that it's a solution somewhere between 0 and pi over 2 radians. So think about your unit circle. When is the value of sine, which is the y-coordinate, equal to 1/2? That's at pi over 6 radians. So that is alpha, our lower limit of integration. Turns out this corresponds to pi over 6 radians. So now we have a plan. So we just need to execute it. So again, lower limit of integration when you're finding area between two curves comes from setting your two expressions of theta equal to one another. So the area between those graphs, let's think about how we can find that. If area in general enclosed by a polar curve is given by that 1/2 f of theta squared integral. So the area inside the circle here, so the area enclosed by the circle, would be given by area inside the circle would be given by 1/2 integral from pi over 6 to pi over 2 of f of theta, which for the circle, that's 3 sine theta squared d theta. That would give you the area inside the circle. But so area inside the circle between these two rays is going to include the area inside that cardioid. So we want to subtract the area inside the cardioid so that we end up with just this area outside. So we need to do the area inside the blue, which is what I've set up so far, minus the area inside that red curve. So minus the area inside the cardioid, which is given by 1/2 integral from pi over 6 to pi over 2 of the expression for the cardioid squared. So 1 plus sine theta all squared. So to find the area of the region between those two graphs, we could combine that. They both have a coefficient of 1/2. Oops, I got too many lids here. So this minus this, I could factor out the 1/2. And where did the eraser go now? Oh, here it is. Factor out the 1/2, and then I'll have integral here minus this integral. We could combine that into a single integral. So let me back this up. I want to make sure that I have enough room here. Also keep in mind that if we're integrating pi over 6 to pi over 2, we're just getting half of that total area. So we still need to multiply by 2 to get the total area. So 2 times, we factor out the 1/2, integral from pi over 6 to pi over 2 of the area inside the circle, which is this 3 sine theta squared. So I'm going to go ahead and call that 9 sine squared theta, minus the area inside the cardioid. So the 1 plus sine theta all squared. And I'm going to need to get rid of this. So we're replacing this expression over here with a single integral. So in this case, 1 plus sine theta. That f of theta squared. Okay, all integrated with respect to theta. So one thing here, just in general, when you want to find the area between two polar curves, you'll do your outer polar curve squared minus your inner polar curve squared. So outer minus inner, each of those is squared. Okay, so now we just have to evaluate this integral. Let's see what we can do. Well, the 2 times 1/2, so that's fortunate. So our coefficient in the front is now just 1. Integral from pi over 6 to pi over 2 of 9 sine squared theta minus, okay, so when we multiply this out, we'll have 1 plus 2 sine theta plus sine theta squared. Okay, integrated with respect to theta. So that's integral from pi over 6 to pi over 2, 9 sine squared minus sine squared when you distribute the negative here. So that'll give us 8 sine squared minus 1 minus 2 sine theta. Okay, so in order to integrate it, this can be integrated directly, this can be integrated directly, but in order to integrate that sine squared, here again, you're going to need to do power reduction. So in order to evaluate this integral, we have to apply power reduction again. And so that sine squared becomes 1/2 1 minus cosine of double that angle. Okay. And we've still got pi over 2. We still got an 8 in front of that, so that'll be 4. Minus 1 minus 2 sine theta d theta. Okay, let's go ahead and write an antiderivative. So I'm going to come back up here. So for the antiderivative, 8 times 1/2, so that's 4, times the antiderivative of 1 with respect to theta, so that's theta, minus the antiderivative of cosine of 2 theta, so that's what, there would be sine of 2 theta times 1/2, 1 over this number here. So 1/2 sine of 2 theta. Remember, you can always check by taking the derivative of this. Derivative of sine is cosine. 2 theta times 2 would cancel this. And again, this 8 times 1/2, this is 4. That's the 4 I put right here. So we're good. We got an antiderivative of this piece minus antiderivative of 1. So that's easy. That's theta. Minus 2 times the antiderivative of sine is negative cosine. Okay. Evaluated from pi over 6 to pi over 2. Okay, I'm going to clean this up a little bit. So if I distribute the 4 here, this will be 4 theta minus theta. I'm going to go ahead and combine those, so that's 3 theta. Minus 4 times this, so that'll be 2 sine of 2 theta. I've already combined that with this 4 theta up here, so now this will be positive 2 cosine of theta. Okay, evaluated from pi over 6 to pi over 2. Now we can crunch the numbers. So this will be 3 times theta minus 2 sine of 2 times theta plus 2 times cosine of theta. Let's see. 2 times cosine of theta. Okay, great. Too bad. I guess the graph is going to have to go. Get rid of all the rest of this while we're at it. Okay, so that's plugging in pi over 2. Minus what you get when you plug in pi over 6. So that's 3 times pi over 6 minus 2 times sine of 2 times pi over 6 plus 2 times cosine of pi over 6. Right. We good there. So this is 3 pi over 2. Sine of pi is 0. Cosine of pi over 2 is 0. 3 pi over 6 here. Which is, well, let's go ahead and reduce that. Why call it 3 pi over 6? So that's minus pi over 2 when you reduce it. I'll keep this here. Minus 2 times sine of, this will reduce to pi over 3. And sine of pi over 3 is the square root of 3 over 2. Plus 2 times cosine of pi over 6 is the square root of 3 over 2. So minus 2 over 2 square root of 3 over 2. Well, here, minus square root of 3 plus square root of 3, these are going to cancel out. And so what do we have? 3 pi over 2 minus 0 plus 0 minus pi over 2. And then the square root of 3's canceled each other out. So 3 pi minus 1 pi, this is 2 pi over 2. So our final answer is pi square units enclosed in that graph.